Hello everyone. If you're watching this, then you've missed day one of our week 13 lecture, or just looking back on it. I think lots of people will be because we had a shortened class period and we had a lot to cover. So let's get to it. We skipped the warm-up for today, but you can check out a short video that's part of this PowerPoint presentation that was going to be our warm-up. We covered truth tables and De Morgan's laws, and you have an assignment for those due Wednesday at midnight, right before the break. You should be able to construct and read a truth table, evaluate Zohr statements, and use De Morgan's laws. Let's get to it. So the first thing we talked about was truth tables. Truth tables are a way for you to figure out various possible combinations or evaluations of combinations of variables. So you always start them the same way, and then you add on whatever other entries you want to evaluate your specific expression. So they could be things with ors, ands, nots, zors, whatever. All of that stuff goes over here, and then you use what you know about the combinations of trues and falses to figure out a specific evaluation for each following entry. For a one-variable truth table, there's only two options, true or false. It's a very boring, very much not very useful construction. For two variables, we've got four possible combinations. True, one of them being false, or both false. For three variables, well, you might be catching on to a pattern here. It doubles. We have 8 entries. Whoa, that's a lot. So we try not to have too many questions with those. I value your time, but this would be something that could come up in the future. So this should be something you can do. You don't have to memorize this table by any means, but if you want to reconstruct it, there's a pattern here. You have 4 trues, 4 falses, then 2 trues, 2 falses, 2 trues, 2 falses, and then alternating every other one. And you could keep going and construct a table for 4 or more just by increasing that pattern farther. Now, we didn't talk about knots in a whole lot of depth last time, so I just want to quickly mention them again. A not operator simply negates whatever you give it. It can be written as an exclamation point or one of these squiggly lines, which can be found right above the tab key on your keyboard. A not true becomes false, a not false becomes true. There's one other operator we haven't mentioned yet, and that's an exclusive OR. An exclusive OR, or an XOR, is very much like an OR in that it evaluates to true if one of its inputs is true, but it has the distinct difference where if you feed it 2 trues, it gives you out a false. So that is the only difference between an exclusive OR and a regular OR. Very interesting operation. So armed with that knowledge, let's take a look at your assignment that's due Wednesday. It is posted on MyMCPS under week 13. It's titled 040501 Boolean Logic. What do you have to do? You have to construct some truth tables for me. Now, the first thing that you'll notice is I messed up. Obviously, this first truth table is missing a column for the B variable, which is very important to have, otherwise you can't calculate anything. So I'm going to insert another column here and put an 8B there. All right, so how do we do this? First, we just combine every possibility of A and B being true or false right here in the table. True, 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 false, false, true, or false, false. Now, what are we actually using this truth table for? Well, in these first 7 questions, I'm asking you to draw the truth table and figure out if this expression is valid or not. So what do I mean by that? This arrow here implies that anything you could input into the left-hand side should give you the same result if you input it into the right-hand side. So we'll know if this is true or not, or valid or not is a better way to say it, so you don't get confused with individual truths, if our truth table has the same exact entries for all of this as it does for A. If it does, that means we can just write A instead of all of this, and that would be valid. So let's see how this goes. Let's figure out A or B. So remember, for OR, as long as one thing is true, the whole statement is true. So we have true, true, true. Two falses make a false. Okay, so now we can evaluate A and A or B. Sometimes people like to substitute in a different letter here just to help them kind of visualize this as an easier problem. So you could say maybe A or B, well, we'll call that variable C, and then you're just evaluating A and C, right? It's the same exact idea. You don't have to do that. It's just something that helps some people visualize. So we're doing this quantity here, combined with an and with this quantity. Let's see what happens. True and true gives us true. True and true gives us true. False and true gives us false. And false gives us false. Now let's look at this. This column over here is the right-hand side of our equivalence relation. This column here is the left-hand side. Notice that they are identical. True, 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 false, 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 false. That means this is a valid equivalence relation. We don't have to write out all of this. Just writing out A by itself would give you the same result. For the second one, you can insert a column to the right, because we will need a total of 5 columns. We would need to figure out A, B, A and B, A or A and B, and last but not least, A or B. So hopefully the pattern is catching on here. I'm just going to go ahead and reveal the answer, because this is a case where it's not a valid equivalence relation, and I want to point out why. So we're going to have true, true, false, false, true, false, true, false. You don't have to write these out in this order. This is just a convention that's common. As long as you've listed every possibility, you're all set. There's a total of 4 possibilities there. All right, true, false, false, false for A and B. For A or A and B, we're going to look at this column and try to combine them with an and. Well, this first one is true. The rest have a false, so they cannot be true. And last but not least, we have A or B. So we have a true, 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 false. Oh, I apologize. Since this is an or, this should be a true as well, since we have a true right here. My bad. This is the correct answer. All right. So what do we have here? This is almost identical between these two columns, but right here, this is a false and this is a true. That means this is not a valid equivalence relation. Not valid. What makes it not valid is this possibility where the left-hand side and the right-hand side could evaluate to different things. Left-hand side evaluates the true, right-hand side evaluates the false, right-hand side evaluates the true. They're not the same. Therefore, this is not an equivalence relation. Despite the fact that 75% of the time it does evaluate to the same thing, even this one single discrepancy is enough to invalidate the whole thing. In fact, if this was a 1,000-line long truth table with lots of variables, and all of them came out to be equivalent except for one line, it would still not be a valid relation. So you have to be very careful, make sure everything matches up. If it doesn't, it's not valid. We've got the rest of these to work through. There's a couple more things to mention. The first thing to mention, that we haven't quite gotten to, is De Morgan's law. So De Morgan was a old European mathematician, and he came up with this idea that you could actually take negation, and there's an equivalence relation with it that's really useful, that essentially acts very similar to distributive property in mathematics. You're almost like distributing the negation to each of the elements within the parenthesis, and then you're switching the operation between them. That part is different from mathematics, but it is true in logic. An and becomes an or, and an or, as you can see, becomes an and. So let's go ahead and give this a shot in practice. One kind of thing that can be very useful when writing these really long, complicated things is we can rewrite symbols for and as just a multiplication. And in multiplication, oftentimes we'll put variables next to each other if we're multiplying them. So this simply means A and B, and we'll put a plus instead of or. And the reason these are popular is and has distributive properties similar to multiplication. So for instance, if we have A and quantity C or D, we could say that's the same exact thing as A and C or the quantity A and D. And same thing with or it can have various properties that are similar to addition, such as it doesn't matter which or statement we evaluate first, you'll still get the same answer. So, Martin, with that knowledge, let's go ahead and take a look at a De Morgan's law. That's a little bit tricky, so I'm going to do this one on the board here, and you have one question on your homework that involves this idea, so hopefully you can figure it out there. All right, so how do we do this? We're going to essentially distribute, really you're using De Morgan's law, this negation to each of the elements inside your parenthesis. So we've got this one, last but not least, this one. Now there's 3 elements here. De Morgan's law can work with more than 2 elements. As many elements as you want, as long as they're within your parentheses like this, it's going to be perfectly valid. So how do we do it? We negate the first element, A or C. Remember, the plus just means or. That invisible multiplication symbol here that means and needs to switch because we're using De Morgan's law. And it becomes an or. And we have quantity of not C and D. And last but not least, there's another multiplication here meaning and that becomes an or. So we should get or E. And the E is also negated. So not E. All right. Now, the tricky thing is you can apply it again if you really wanted to. So we could once again say, okay, let's do Morgan's law, this part of our equation, this part. There's nothing to do here. That one's done. So let's see. We could say this is the same thing as not A, and this or becomes an and, not C. Ta-da! Then over here, we still have this or, but we can use De Morgan's law to get not C or not D. This and becomes an or. And last but not least, we're not going to touch that not E. It stays the same. So De Morgan's law tells us that these 2 quantities are equivalent. And you could construct a truth table, if you were really bored, and double check that this is the case. Anything you put in here will give you the same exact output as anything you put in here. That is all we talked about. Please let me know if you have any troubles on that assignment or need extra help. I'd be happy to assist you. Send me an email and we can find some time to meet. Otherwise, I hope you have a fantastic Thanksgiving, and I'll see you guys next week. Take it easy.